On a cold Christmas day in 1642, in a small farmhouse in Woolsthorpe, England, a tiny baby was born. His name was Isaac Newton. No one could have guessed that this small, quiet boy would grow up to change the world. His early life was not easy. He was born prematurely, and his father had died before he was even born. He grew up on a farm, and for a time, it seemed his destiny was to be a farmer, just like his father. But young Isaac's mind was not on the fields. It was always somewhere else, lost in thought, looking up at the stars and wondering about the world around him. He was a curious child, always building little models and machines, trying to understand how things worked. This innate curiosity was the seed of a genius that would eventually blossom and reshape our understanding of the universe itself. Newton's school days were a mix of quiet observation and brilliant insights. He wasn't always the top student in his class, but his mind worked in a different way. He was fascinated by the patterns he saw in nature, from the way the sun cast shadows to the flight of a bird. He filled notebooks with his questions and his drawings, trying to make sense of the world. One famous story tells of him building a small windmill that could actually grind flour, powered by a mouse on a tiny treadmill. This was the kind of mind he had, practical, inventive, and relentlessly questioning. He didn't just accept the world as it was presented to him. He wanted to take it apart, piece by piece, and understand the fundamental rules that governed its every movement and every change. His teachers soon noticed his extraordinary talent, and they encouraged him to pursue his studies. With the help of his uncle, Newton was able to go to the University of Cambridge. This was a turning point in his life. At Cambridge, he was finally in an environment where his powerful intellect could be nurtured. He threw himself into his studies, reading the works of the great thinkers who came before him, from Aristotle to Galileo. But he wasn't content to just read their ideas. He wanted to test them, improve upon them, and push the boundaries of knowledge further than anyone had before. He was on the verge of a series of discoveries that would not just make him famous, but would lay the very foundation for modern science, giving us a new way to see the cosmos. The world at that time was emerging from an age of mystery and superstition, and Newton was one of the key figures who would light the way forward with reason and evidence. When the Great Plague forced Cambridge University to close in 1665, Newton returned to his family farm in Woolsthorpe. It was during this period of isolation, his year of wonders, that his genius truly ignited. Away from the distractions of university life, he had the time and the space to think deeply about the biggest questions in science. It was here, sitting in his garden, that he supposedly watched an apple fall from a tree. This simple event sparked a profound question in his mind. If the force of gravity could pull an apple to the ground, could that same force reach all the way to the moon and keep it in its orbit? This was the beginning of his revolutionary theory of universal gravitation. Isaac Newton gave us a set of rules that describe how everything in the universe moves. These are his famous 3 laws of motion, and they are so fundamental that we still use them today to send rockets into space. The first law is about inertia. It says that an object will stay still or keep moving in a straight line at a constant speed unless a force acts on it. A football on the grass won't move until you kick it. The second law explains what happens when a force does act on an object. It tells us that the more force you use, the faster the object will accelerate. It also says that it's easier to move a lighter object than a heavier one. This simple idea is expressed in the famous equation F equals ma, or force equals mass times acceleration. The third law of motion is perhaps the most elegant. For every action, there is an equal and opposite reaction. Think about a rocket launching into space. It pushes hot gas downwards with incredible force. In return, an equal and opposite force pushes the rocket upwards, lifting it off the ground and towards the stars. These 3 laws, when put together, provide a complete picture of why things move the way they do. They took the guesswork out of mechanics and turned it into a precise science. Newton's laws allow us to predict the path of a planet, the trajectory of a cannonball, and the orbit of a satellite with incredible accuracy. They are the bedrock of classical physics, a powerful toolkit for understanding our world. But Newton's genius didn't stop with motion. He was also fascinated by light. At the time, people thought that white light was pure and simple. Newton, however, had a different idea. In a darkened room, he let a single beam of sunlight pass through a glass prism. The result was spectacular. The prism split the white light into a beautiful rainbow of colors: red, orange, yellow, green, blue, indigo, and violet. This showed that white light isn't pure at all. It's actually a mixture of all the colors of the spectrum. He then used a second prism to gather all the colors back together, and they reformed into a single beam of white light, proving his theory beyond doubt. This discovery revolutionized our understanding of optics. It explained why we see colors. An object looks red because it absorbs all the other colors of the spectrum and reflects only the red light back to our eyes. This insight had practical applications too. Newton realized that traditional telescopes, which used lenses, had a problem. As light passed through the lens, it would split slightly, just like in his prism experiment, creating a fuzzy, rainbow-colored halo around the stars. To solve this, he invented a completely new kind of telescope. Instead of a lens, he used a curved mirror to gather and focus the light. This reflecting telescope produced much sharper and clearer images, and it is a design that is still used in many of the world's most powerful telescopes today, including the Hubble Space Telescope. To describe the universe he was uncovering, Newton needed a new kind of mathematics. The maths that existed at the time was good for describing things that were static and unchanging, but the universe is a place of constant change. Planets are always moving, objects are always accelerating or decelerating, and things are always growing or shrinking. To understand this dynamic world, Newton needed a mathematical language that could describe change itself. So, in one of the greatest achievements of the human mind, he invented one. We call it calculus. It is, in essence, the mathematics of motion and change, a powerful tool that allows us to analyze systems that are in a constant state of flux. Calculus is built on two big ideas: differentiation and integration. Differentiation is like having a mathematical microscope that allows you to look at a single moment in time. It lets you calculate the exact rate of change at any given instant. For example, if you know the path of a moving planet, differentiation can tell you its precise speed and direction at any point in its orbit. It's the tool that measures instantaneous change. It helps us understand how things are changing right now, whether it's the speed of a car, the growth of a population, or the cooling of a cup of tea. It's a fundamental concept that underpins much of modern science and engineering. Integration is the other side of the coin. If differentiation is about breaking things down into tiny moments, integration is about adding them all up. It allows you to calculate the total effect of a series of continuous changes over time. For example, if you know the changing speed of a rocket, integration can tell you the total distance it has traveled. It can also be used to find the area of complex curved shapes or the volume of irregular objects. Together, differentiation and integration are like two halves of a whole, providing a complete framework for understanding and predicting the behavior of dynamic systems. It is the language that nature itself seems to speak. The invention of calculus was absolutely essential for Newton's work in physics. Without it, he could never have fully developed his laws of motion and universal gravitation into a precise predictive theory. It was the mathematical engine that powered his scientific revolution. It allowed him to prove that the force of gravity that pulls an apple to the ground is the very same force that keeps the planets in their elliptical orbits around the sun. This was a monumental breakthrough. For the first time, humanity had a single universal law that could explain phenomena both on Earth and in the heavens. Calculus gave Newton the power to write down the laws of the universe in the form of elegant, powerful equations. Newton didn't keep his incredible discoveries to himself. He compiled his life's work on motion and gravity into one of the most important books ever written, Philosophiae Naturalis Principia Mathematica, or simply the Principia. Published in 1687, this book laid out his laws of motion and his theory of universal gravitation in meticulous detail. It was written in the language of geometry and calculus, and it was a breathtaking achievement. In the Principia, Newton demonstrated how a single set of principles could explain the falling of an apple, the tides of the oceans, the paths of comets, and the majestic dance of the planets. It presented the universe as a grand mechanical system, a giant clockwork governed by precise, predictable, and knowable laws. The impact of the Principia was immediate and profound. It completely reshaped the scientific landscape and kicked off a new era of scientific inquiry known as the Enlightenment. Before Newton, the heavens were seen as a place of mystery, governed by different rules from those on Earth. After Newton, the universe was seen as a single, unified system that could be understood through reason and mathematics. Scientists now had a framework and a set of tools to explore the cosmos. The book provided a blueprint for the scientific method, emphasizing the importance of observation, experimentation, and mathematical proof. It gave humanity the confidence to believe that we could, through science, unravel the deepest secrets of nature. Newton also published another hugely influential book called Optics in 1704. In this book, he detailed his decades of experiments with light and color. He described how he used prisms to decompose and recompose white light, and he discussed his theory that light is made of tiny particles, which he called corpuscles. While we now know that light has a dual nature, behaving as both a particle and a wave, Newton's work in optics was groundbreaking. It was written in a more accessible style than the Principia, and it inspired generations of scientists to study the nature of light, leading to the development of fields like spectroscopy, which allows us to determine what stars are made of just by analyzing their light. Today, more than 300 years after he lived, Isaac Newton's legacy is all around us. His laws of motion are still the foundation of engineering, used to design everything from bridges and cars to aeroplanes and spacecraft. His invention of calculus remains an essential tool in virtually every branch of science, technology, and economics. The reflecting telescope he designed is the basis for the giant observatories that peer into the farthest reaches of the universe. He showed us that the universe is not a chaotic, unpredictable place, but an orderly and understandable one. His work gave us a profound sense of our place in the cosmos and empowered us to explore it. As he famously said, "If I have seen further, it is by standing on the shoulders of giants." But in the story of science, Isaac Newton is, without a doubt, one of the greatest giants of them all.